All right, we're going to continue solving trig equations. They're just going to get a little bit more difficult today, and we're also going to talk about how to write our answers so that they include all of the solutions. So if we look at that first one, it's the exact same process that we had been doing. We're going to get cosine of x by itself, so we're going to add 1 to both sides and then divide by 2. So we have cosine of x equals 1/2. So think back to your unit circle. Where does the cosine of x equal 1/2? That would be at pi over 3 and 5 pi over 3. Now, if we think of a unit circle, here's my pi over 3. Well, I can go here, and what if I go around another time? And another time, and another time. As long as I'm landing on that reference angle, those are all answers. So what we're going to do, I'm adding a circle each time, which is equivalent to 2 pi. So we're going to take pi over 3 plus 2 pi n. That n represents how many times we go around. Same thing with the other one. 5 pi over 3 plus 2 pi n. Now, let's also think about this the other way. If that's my reference angle, what if I go backwards? What if we go this way? Do I still land at that reference angle? I sure do. So really we have plus or minus 2 pi n, and these represent all of the solutions. Let's look at the second one. Now the second one has multiple cosines in it. So I'm going to get the cosines on one side. So I'm going to add cosine of x, which leaves me with 2 cosine of x. Now I'm going to solve it, so I'm going to subtract radical 2. And then divide by 2. Okay, on the unit circle, cosine is negative, where the x values are negative. So my solutions for this will be 3 pi over 4 and 5 pi over 4. And then again, we have their plus or minus 2 pi n plus or minus 2 pi n to represent all of the solutions. Try the third one. I'm going to add 1 to both sides. Multiply by 3, so we have tan squared of x equals 3. This one's a little bit different because we have to square root both sides, and when we square root, remember when we're solving and we square root, we have to remember our plus and minus. So we have plus and minus the square root of 3. So that's all of the values where tan equals the square root of 3 or negative square root of 3, which will be pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. And again, all of the solutions would mean we would add that 2 pi n to each of these. And that represents all of the solutions for that one. Let's look at number 4. Now, number 4 is a little bit different. We're going to get everything on one side, and now we're going to have to start thinking about factoring as we look into these. So I'm going to subtract that 2 tan squared over to the other side. And for this one, factoring, always look for that GCF. These have a GCF of tan squared. So I'm going to pull out, or a tan x, I'm going to pull out a tan x, which means I'm left with sine squared x minus 2. Now, just like before when we had quadratics, you're going to take each of these and set them equal to 0. So we have tan x equals 0, and we have sine squared x minus 2 equals 0, which is really sine squared x equals 2. Well, where does tan x equal 0? Tan x equals 0 at 0. So essentially, it's here and here, and all the reference angles from there to there, all the way around. So we're just going to write that as plus or minus n pi, because we just add a pi to get to the next one, add a pi, add a pi, add a pi. Now, where on the reference circle does sine, oh, we forgot to square root. So let's square root both sides. So we have sine x equals plus or minus square root of 2. Where does sine squared or sine x equals square root of 2? It doesn't. So there's no solutions for that part. So those are your answers. Let's look at another one. Okay, now think back to factoring. Think of this equation just like as if we would have 2x squared minus x minus 1. If we were going to factor that, what would we do? Well, what times what is 2x squared? 2x and x. What times what is 1? 1 and 1. They multiply to be a negative, so they have to be opposite signs. Our middle term has to be minus x, so we have a 1x and a negative 2x. 1 plus negative 2 is negative 1, so that's factored. So now instead of x's, let's put in cosines. So when I factor over here, I have 2, I didn't leave enough room. We're going to do the exact same thing. We're going to do 2 cosine x plus 1, and then cosine x minus 1. It's factored just like it was before. Now, just like we had been before, we're going to take one parenthesis, set it equal to 0, and solve. And then we're going to take our other parenthesis and set it equal to 0 and solve. So the first one comes out to cosine x equals negative 1/2. The second one comes out to cosine of x equals 1. All right, so let's look at the first one. For the first one, when does cosine x equals negative 1/2? That would be at 2 pi over 3 and 4 pi over 3. Where does cosine x equal 1? Well, that's right here, 0. So 0 plus or minus 2n is just plus or minus 2n. Whoop, 2 pi n. Go ahead and add in that to your other ones. And there's all of your answers. Now, for this next one, I'm going to introduce Pythagorean identities. So look over here on the right. You need to write these down. These are going to start creeping in anytime that we need to replace a sine squared, cosine squared, secant squared, tangent squared, and so on. So let's look at number 6 with those. When I look at number 6, do you notice how we have a cosine squared and a sine? That's a problem. We can't do anything when we have two different variables, right? Same thing when we have two different trig functions. So we're going to have to change one of those. Well, if I look at these Pythagorean identities, I see that this first one has to do with sine and cosine. Well, I do have a cosine squared right here, so let's see if we can maybe change him. So I have sine squared theta plus cosine squared theta equals 1. I'm going to solve down for cosine squared theta and see if we can use some substitution. So cosine squared theta equals 1 minus sine squared theta. So I'm going to substitute this in since it equals cosine squared theta, and I'm going to put it in for cosine squared. So now we have 2 times 1 minus sine squared x plus 3 sine x minus 3. Let's simplify it down. So I'm going to distribute my 2. I have 2 minus 2 sine squared x. Bring everything else down. Combine those like terms. So negative 2 sine squared x plus 3 sine x minus 1. Now remember, when we're factoring, when it's equal to 0, we can get rid of that negative that's out in front of the x squared by dividing everything by a negative, both sides. So really we have 2 sine squared x minus 3 sine x plus 1. Now that we have our quadratic, now we can factor. So I'm going to factor this one, and it actually factors into 2 sine x minus 1 sine x minus 1. Negative times a negative is a positive. And then you can check your middle term. Negative sine, negative 2 sine gives us that negative 3 sine in the middle. Now that we have our two parentheses, now we can set each one equal to 0. So I have 2 sine x minus 1 equals 0. And I have sine x minus 1 equals 0. Solve each one down. So for the first one, we have sine x equals 1/2. Well, where does sine x equal 1/2? That would be pi over 6, so plus 2 pi n to represent all of them, and 5 pi over 6 plus 2 pi n to represent all of them. And then where does, let's see, this one would be sine x equals 1. Where does sine x equal 1? That would be straight up at pi over 2, and to represent all of them, we add on that 2 pi n. So there's all of your solutions for that one. All right, let's look at this one. Now this one, we don't have anything to substitute in yet, but what can we do to manipulate this equation so that we can? Let's see what happens if we square both sides, because we already have those Pythagorean identities, right? So we can substitute stuff in. So if I square both sides, what do I have? I have sine x minus 1 squared equals cosine squared x. Well, what did we say cosine squared x is? It's right here. 1 minus sine squared x. And if I substitute that in, now I have an equation that's down to just sine. Remember, when you square this other side, you actually have to write this twice and FOIL. So when we FOIL, we get sine x squared, or sine squared x, whichever way you want to write that. Let's see. Minus sine x minus sine x plus 1. So sine squared x minus 2 sine x plus 1 equals 1 minus sine squared x. Whew. Now we need to get everything on one side. So when I subtract that 1, those 1's cancel. Now I'm going to add sine squared x, which leaves me with 2 sine squared x minus 2 sine x equals 0. So now this one looks like a quadratic still. We have an x squared, but it's only two terms, and they have some stuff in common. So now I'm going to pull out my GCFs. So my GCFs would be 2 sine x. That leaves me with sine x minus 2. Now that I have those two factors out of the way, I'm going to pull them off to the side. So I have 2 sine x equals 0, and I have sine x minus 2 equals 0. Let's solve both of those down. So on the first one, whoops, this should be a 1. I apologize for that, because we pulled that 2 out. 2 divided by 2 is a 1. All right, so in the first one, we have sine of x equals 0 divided by 2 is 0. On the second one, we have sine of x equals 1. So where does sine of x equal 0? Well, sine of x equals 0 at 0 and pi. And the second one, sine of x equals 1 at pi over 2. Now, I do want to show you one like this because we have to think about what happens when we plug these in. Think back to when we had rational functions and we were solving. You always have to take those solutions and plug them in to make sure that they work, because sometimes they don't. So if we look at this one and we plug 0 in, we end up with sine of 0 minus 1 equals cosine of 0. Well, sine of 0 is 0. 0 minus 1 is negative 1. Cosine of 0 is 1. That's not a solution. So we actually can just take that out. If you plug in the other two, they do work. They're fine. So we can just add in our plus 2 pi in. And those are solutions. So always check your solutions and make sure that they come out. All right, now let's do a couple where we have a number inside with the x, because these are a little bit different. So if we look at number 8, we're going to solve this just like we normally would, and we're going to ignore that 5x. So I'm going to make that 5x become an a. This guy right here is going to be an a. So really I'm going to solve 2 sine of a minus 1 equals 0. So when I do that, I get sine of a equals 1/2. Well, where does sine of a equal 1/2? Sine of a equals 1/2 at pi over 6 and 5 pi over 6. To show all of the answers, we can add in that 2 pi in. But here's the deal. These two guys equal a. But a equals 5x. So really, we have another step to this equation. Really, we have 5x equals pi over 6 plus 2 pi in. And 5x equals 5 pi over 6 plus 2 pi in. So now I need to solve down for x. I have one more step for each one. So I'm going to divide by 5 on both sides. So for the first one, I get pi over 6 divided by 5. Remember our leave it, change it, flip it. Leave it, change it, flip it. So I get pi over 30 plus 2 pi n over 5. And then on my second one, I'm going to divide by 5 again. So I get, remember, 5 over 6, change it to multiplication, flip it. Well, my 5's cancel, so I get pi over 6 plus 2 pi n over 5. And those are all of your solutions. Let's look at one more like that. So on this last one, exact same thing. We're going to make this stuff in here some other variable. Let's call it a. So I have 5 tan of a plus 5 equals 0. When I solve that down, I get tan of a equals -1. Well, where does tan of a equal -1? That would be at 3 pi over 4 and 7 pi over 4. Okay, so then I'm going to add in my 2 pi in so that it represents all of the solutions. And now I need to go back to what a equals, because this stuff equals a. But I have a value for a. So now I'm going to go back to what a equals, and I have pi over, x over 2 equals 3 pi over 4 plus 2 pi n, and x over 2 equals 7 pi over 4 plus 2 pi n. I'm going to solve each of those by multiplying by 2 on both sides to get x equals 2 times 3 is 6. 6 over 4 simplifies, right, to 3 pi over 2 plus 2 times 2 is 4, so 4 pi n. There's some solutions. Then on the other side, we're going to multiply by 2 on both sides again. So we get x equals 2 times 7 is 14. 14 over 4 simplifies to 7 pi over 2 plus 2 times 2 is 4, so 4 pi n. And that is how you solve the more challenging